Recall that we got the logistic equation for population growth by starting with this more basic population model, this unconstrained population growth model, and we modified it because we had this idea that that this equation sort of wasn't capturing the reality of or a certain reality of population growth that we wanted to capture, or a certain feature of population growth that we would expect in the real world. Right? This equation didn't reflect the fact that in reality populations always have some kind of limit to their growth. And so we inserted this extra factor just to produce an extra equilibrium solution that we expected. But this isn't the only kind of modification that we might want to do to a population model. Depending on the context you're working in, there are lots of different modifications you might make. Let's look at a few examples. So for example, suppose that we are harvesting the population at a constant rate. So maybe the population is the number of fish in the sea, and we want to see what would happen to the population if we harvested a certain number of fish every year. So we could start with our logistic equation. So dp dt equals r times p times 1 minus p over k. So to even use this in some applied situation, like with fish in the sea, or a particular population of fish in the sea, you'd have to measure or approximate your growth rate somehow, maybe by observing the fish, and then also measure or approximate the carrying capacity of the environment for that particular species. Okay, so this is our basic logistic model, but how can we modify this to represent harvesting at a constant rate? Well, a constant rate, this would be so many individuals per year, maybe, so per time unit. But that's also, this is the same unit as this rate of change. This is also individuals per year. So, so the rate at which we harvest should just be some number, right? Some number whose units is individuals per year. But when we harvest an individual, we're taking it out of the population. So whatever our rate of harvesting is, we should subtract it, right? This first term gives us, or describes how the population grows. So this is growth. And so harvesting is going to have a minus sign because that causes a shrinking of the population and not a growing of the population. So harvest. But since it's at a constant rate in individuals per year, this is just going to be some number. So we could call it, I don't know, capital H, for example. So if we wanted to model harvesting a population, we could use this this differential equation. All right. So what about a slightly different situation, harvesting at a proportional rate? So we could still start with our logistic differential equation. So dp dt equals r times p times 1 minus p over k. Okay, we're doing some harvesting, so we should subtract. And we need to subtract the number of individuals. So the individuals we harvest per year. So let's call the proportional rate of harvesting, how about little h? When I say it's a proportional rate, what that means is the number of individuals that we harvest per year divided by the size of the population is the constant h. So this is what I mean by a proportional rate. Right? A proportional rate is 1 divided by the size of the population. Well, to get the units to fit in this differential equation, what we need to put in this negative term is just the number of individuals per year that gets harvested. So we can just move this p over here. So here we have our rate of harvesting, our proportional rate of harvesting times p. All right. Now for both of these examples, at this point, we could either solve them explicitly if we are able to solve them explicitly. It kind of depends, whether we have the tools to solve them or not depends on how exactly these differential equations are formed. If we can't solve them exactly, there are numerical methods for approximating solutions. There is one more example of a modification to a population model, to this population model that I want to look at, and that's if there's a population threshold. So, we have this phase line where there's an equilibrium at 0, and there's a carrying capacity. If the population is above the carrying capacity, then it should decrease. If the population is below the carrying capacity, then it could increase. But, if a population is too small, it probably won't grow. If a population is too small, it's possible that individuals in the population will never meet each other, in which case it's impossible for them to reproduce, depending on how that species reproduces. So if the population is too small, it should actually die out instead of increasing. So that means there's some threshold value, which we'll call t, and if the population is below that threshold value, the population actually goes down instead of up. So that would give us a phase line like this. So how could we arrange for this to happen? Well, remember we started with our logistic model. It starts out dp dt equals r times p times 1 minus p over k, right? This p, this factor of p, this gives us the equilibrium at 0. The term 1 minus p over k, this gives us the equilibrium at k. According to this phase line, what we want is another equilibrium at t. So we need some factor here that gives us an equilibrium at t. Okay. So there are lots of possibilities. It might be p minus t, it might be t minus p, it might be 1 minus p over t, right? There are lots of possibilities. So maybe to figure out which one makes more sense, maybe we should sketch a graph of dp dt versus population. So the phase line tells us that this graph should go through 0. It should cross the horizontal axis again at t, and it should cross the horizontal axis a third time at k. Now between the threshold t and the carrying capacity k, the growth rate should be positive. So that means between t and k, our graph should be above the horizontal axis. Above k, the rate of change should be negative, and that means our graph should be below the horizontal axis. Between 0 and t, the graph should be below the horizontal axis because dp dt should be negative, so like this. And when p is less than 0, we don't care what happens because that's not realistic. So we need to write down some shape that gives us this. We need to write down some function that gives us this kind of shape. Well, it looks like what we're heading towards here is a cubic. And our cubic, it needs to go down on the right. So the leading coefficient of this cubic had better be negative. So if we look at the leading coefficients on, or the leading pieces of each term, we have a positive here, right? R is positive. Here we have a negative. So to keep it negative, the term with p in it here should be positive. So we need a p minus something. Okay. But also, right, just like when we decided to have p over k here, we don't want to change the scale of this whole thing, and so probably we should do it this way. So p over t minus 1. So this is going to make it so that the leading coefficient of p is negative, which will mean that this right-hand piece goes down instead of up. And also, if our population is not too far above the threshold, the growth rate is going to be approximately r, although it's not exactly r. So with this differential equation in hand, then we could go try to solve this differential equation, or try to maybe find where this maximum growth rate is, or compute approximate solutions using a computer, or any number of other things, depending on the exact question that you wanted to answer.